Hello, my name is Rasmus Benestad, and I am a climate researcher at the Norwegian Meteorological Institute, and I will give a presentation on lessons learned about the use of downscaled climate model results for practical use, together with Andreas Dobler, Kajsa Parding, and Abdelkader Mesghani. And this presentation was made for the International Conference on Regional Climate Codex 2023 in Trieste. So the objective is to provide or derive robust and reliable information about future climatic outlooks on regional and local scales. But actionable information is still not widely discussed. And we often, for instance, see that only Eurocodex ensembles are provided for in climate services and also for climate change adaptation. We did still, however, we started discussing actionable information in a workshop in Oslo in 2022. The workshop was called ConCord. But if you look at past literature on regional dynamical modeling used for climate services or impact studies, we see that at least for present-day climates, dynamical downscale methods provide little advantage over statistical techniques. And this is a statement from Fowler et al. From 2007. So this is fairly old. But if we look at more recent literature, for instance, the most recent assessment report of the Intergovernmental Panel on Climate Change, then we see that regional climate models do not include all possible Earth system processes and therefore neglect important processes which may influence regional climate projections. And we know that the regional climate models even have to make use of climate adjustment to make sure that they provide temperatures and rainfall that is actually similar to what we observe. And bias adjustment, however, is just a statistical post-processing technique used to pragmatically reduce the mismatch between the statistics of climate model output and observations. It's still quite controversial issue, and we can also see from literature that there are several problems that arise from uncritical use of bias adjustments, and that may even result in misleading impact assessments. In the light of these issues, several authors referred to in the IPCC report dismiss the use of bias adjustment for climate change studies. So when we look at downscaling, we have to distinguish between downscaling weather predictions and climate projections. Because they are different, they require different strategies because they are in different contexts. So when we downscale weather, we want to downscale the actual outcomes, like what is the temperature tomorrow or the day after tomorrow, each day, or the rainfall each day. Whereas when we downscale climate, we want to downscale statistics, which means, like, say, the probability of getting more than 50 millimeters in a year, for instance. So these are quite different sort of approaches and different strategies. Also, we have to note that downscaling is not the same as bias adjustment because it involves grabbing large-scale climatic aspects that the global climate models skillfully reproduce, and then we want to add information to this information about dependencies linking to local climate and also the effect of geographical conditions. One thing is that downscaling or statistical downscaling often use multiple variable predictors. So you use several predictors And that is suitable for weather, but not for climate. Because for weather, when they want to make a downscaling for the next day or next season, we know that the climate doesn't change very much because it's over such a short time horizon. But for climate change, then different predictors may change independently or in a different way to others in different directions. And then it's hard for statistical models calibrated on a set of variables that change in a way that in different directions to others. And one example for this is when we look at downscale storm track densities based on the sea level pressure or the 500 geopotential heights. And both actually give very skillful calibrations, but they give different results because they evolve differently. There's a trend in geopotential height because the temperature in the atmosphere increases. Another aspect is that we need to include natural variability, which is non-stochastic. And using a small number of models will fail to do that. And one example here is a demonstration that was provided by Deseret al. In 2012, where they showed with one climate model that you can get a range of different outlooks purely by having a slight difference in the initial conditions in the atmosphere. And this is important on a local or regional scale, but not on a global scale. As you see here, the global scale, on a global scale, they give very similar results. But on a more local scale, you get like the spread between the weakest and the most pronounced increase is quite large. So you need many models in order to get a good spread of possible outcomes. If you have an ensemble that is too small, then you don't get robust statistics, and this can be explained by the law of small numbers. And here's one example of regional temperature for the Nordic region. Here's one simulation, and then we can do another simulation with the same model, and it gives different results. And the same model will give different results if you run many times like this, and you get like a band of different temperatures. But you see that when you get like a large ensemble, it doesn't matter much if you add a new model because they all show a bigger picture. And then also, if we want to focus on extremes like the highs or lows, then it's important to get a whole range and all the possible outcomes related to natural variability and decadal variability. The same thing, and if you have a different model, you see that the models differ as well, and some of them have quite pronounced decadal variability, at least in the past as well. Same thing for precipitation. Here's one simulation, and you have another simulation. You get quite different evolutions here, and then you need to have a large ensemble. So this is one model, and then two different models. So you see that you get more robust results. So relevant factors for practitioners is that there's non-deterministic internal variability on regional climate scales that we need to take into account. Another question is issue is that the different models have different climate sensitivity, and this may be related to skill or how skillful the models are. Come a little bit back to skill in a moment. Then we have different future emissions that also plays a role, and also the results may be sensitive to methodology, which I showed already, like if how you approach downscaling, at least both for dynamical and statistical downscaling. So here's one example of evaluation of global climate models. These are inspired by the predictors of statistical downscaling. So we evaluate ensembles here, based on patterns of variability. So here you see a pattern of or the magnitude of the mean seasonal cycle in temperature. So it's strongest in the interior in the east and weakest in the oceans in the west here. This is also based on what is called common EOFs that Tim Barnett introduced in 1999. And surprisingly, it's not being used a lot, even though it's a very elegant and efficient way of doing evaluations there. Here we have the leading mode here explains 96% of the variance, so it's basically more or less this is all what is happening. And then we have the black line here is the ERA 5 reanalysis. The red is ERA CMIP 5, that's a previous CMIP ensembles, and then the green is CMIP 6. And we see that CMIP 6 is more tightly clustered around the reanalysis, and it's closer to the truth. And here we have the same thing for precipitation. The leading mode is slightly it's not as dominant anymore, but still we see that CMIP 6 is an improvement over the CMIP 5 as well. And then here is the mean sea level pressure, and we see still that the CMIP 6 is superior here. We can do this also for interannual variability. So here's for temperature. And we see that the CMIP models actually do includes the ERA 5 data reanalysis. So it's doing a fairly good job. And also for precipitation as well. But now the leading EOF represents a much lower fraction of the variance, so we need to include more components here as well. So I want to say that we need to use both dynamical and empirical statistical downscaling when we derive data for and information for practitioners. And the reason for that is that they are based on different sets of assumptions, and they have different strengths and weaknesses. And we could consider them as different tools, and we need all the different tools in order to provide information as well. So we need to make use of all the available information, and then by combining dynamical downscaling and empirical statistical downscaling. In this case here is bias-corrected Eurocodex, and we have statistical downscales. So the blue graph here shows the dynamical downscale based on Eurocodex, and the red curve here shows statistical downscale for the same global climate models. And we see that they have quite similar results. So then we think that the evolution is credible because they're based on different assumptions. But we see that they only represent a small part of the possible range of all climate models here in the yellow. So we need many climate models in order to get the whole range of possible outlooks. And statistical downscaling can be used to extend regional climate model outputs to cover the full range of opportunities. And we want to provide information as opposed to data. So for instance, summary statistics. And when we look at statistically downscaled CMIP 6 ensembles, we see that they are close to being normally distributed. And if they are so, then we only need two parameters, the ensemble mean and ensemble standard deviation, to actually represent the information, or most of the information that is embedded in this. But we need large ensembles to avoid the law of small numbers. And here's one example. We can make maps of temperature, but also like precipitation, showing statistical properties. So this one here is a large multimodal ensemble of 151 runs. It shows the 95 percentile of the winter temperature for year 2050. But when we have these large model ensembles, we need a new model for archiving the big data. And we have more than 1,000 downscale runs at an 8 by 8 kilometer grid. But by using common EOFs to store the information, the essential information, we can actually store this in a smaller space than having the traditional netcdf file for each of these runs there. It's much faster also to derive information. So the summary and here is that we can provide a basis. We have a basis for providing climate information for society that is robust and actionable in many cases. Well, we need to adopt climate information for real. There's a question of how to adopt climate information for real world decisions. Some of the obvious things is to make sure that we overcome the law of small numbers, having robust results, and also we need to overcome the model scale, minimum skill for scales through downscaling, and then it gets more complicated. We also need to understand users' need and capacities, and this can be done through asking questions about what information have they used before, and how have they used it, and why. And this is part of co-production of knowledge. So this has to be like an iterative process, that we discuss all the time and try and see if what the information we provide is good enough. And that will also include capacity. That will also involve capacity building, training, and education and interaction. And finally, here are some references for this presentation. Thank you.